Welcome to Chapter 4, the final chapter of the Intermediate Spintronics series. In this chapter, we'll explore cutting-edge research topics that represent the future of spintronics. We'll cover anti-ferromagnetic spintronics with terahertz potential, topologically protected magnetic skyamions, emerging two-dimensional magnetic materials, and topological spintronics exploiting exotic quantum effects. Antiferromagnets have adjacent spins aligned anti-parallel, resulting in zero net magnetization. While traditionally considered passive materials, they're now recognized as active spintronics components. Key advantages include no stray field for dense packing, terahertz operating frequencies enabled by strong exchange coupling, and robustness against external magnetic fields. Materials like nickel oxide, manganese to gold, and copper-manganese arsenide are actively studied. Antiferromagnets can operate at terahertz frequencies due to their strong exchange interaction. The resonance frequency scales as the square root of exchange field times anisotropy field. Since exchange fields can be 100 to 1000 Tesla equivalent, much larger than anisotropy, resonance frequencies reach terahertz. This is 2 orders of magnitude faster than ferromagnetic gigahertz operation, promising for ultra-fast computing. Antiferromagnetic spintronics faces 2 main challenges. Reading is difficult because zero net magnetization means TMR and GMR don't apply. Solutions include tunneling anisotropic magnetoresistance and anomalous Hall effects. Writing requires manipulating the Neal vector rather than net magnetization. Solutions include spin-orbit torque from adjacent heavy metals and optical switching with femtosecond lasers. QMN as memory was demonstrated at room temperature in 2016. Magnetic skyamions are nanoscale vortex-like spin textures with topological protection. Their non-trivial topology, characterized by integer topological charge Q, makes them stable against local perturbations. Key features include sizes down to a few nanometers, current-driven motion at ultra-low current densities, and non-volatile nature. Applications include racetrack memory, logic devices, and neuromorphic computing. Skyamions come in different types based on their spin rotation pattern. Neal-type skyamions have radial spin rotation and are found at heavy metal ferromagnet interfaces where interfacial DMI dominates. Block-type skyamions have circular spin rotation and appear in bulk chiral magnets with bulk DMI. Anti-skyamions wind the opposite way, so their topological charge carries the opposite sign, and they require low-symmetry crystals with anisotropic d-xyloxone-sciamoria interaction. Current-driven skyamions exhibit unique dynamics due to the skyamion Hall effect. Unlike domain walls that move along the current direction, skyamions move at an angle determined by the ratio of gyroscopic to dissipative forces. Low damping materials have large Hall angles exceeding 80 degrees. This is a challenge for racetrack memory, as skyamions may exit track edges, requiring careful design or antiferromagnetic skyamions. Skyamions enable novel device concepts. Racetrack memory uses skyamions as data bits shifted by current pulses, enabling 3-dimensional storage with unprecedented density. Logic devices implement Boolean operations using skyamion track geometry. Neuromorphic computing uses skyamions as artificial synapses with analog tunability based on skyamion count. The small size and low drive current give advantages over domain wall devices. The 2017 discovery of magnetism in atomically thin chromium triiodide and chromium-germanium telluride opened a new frontier. These van der Waals materials can be exfoliated to single layers while maintaining magnetic order. Unique properties include thickness-dependent magnetism, where monolayer and bilayer can have different behavior, gate tunability of magnetic properties, and compatibility with other 2D materials for heterostructure engineering. Different 2D magnets have varying transition temperatures. Early discoveries like chromium triiodide at 45 Kelvin and chromium-germanium telluride at 66 Kelvin require cryogenic operation. Progress toward room temperature includes iron germanium telluride at 220 Kelvin in bulk, and chromium telluride films reported near 300 Kelvin. Room temperature order has also been reported in vanadium diselenide monolayers, though that result is still debated. Active research continues to find stable room temperature 2D magnets that would enable practical applications. 2D magnets enable novel spintronic devices. Ultrathin MTJs with atomic layer magnets represent the ultimate scaling limit for MRAM. Chromium triiodide spin valves exploit the interlayer antiferromagnetic coupling to achieve giant tunnel magnetoresistance. Spin transistors use gate voltage to switch magnetic order electrically. The atomically sharp van der Waals interfaces avoid intermixing problems of conventional thin films. Challenges include low transition temperatures and air sensitivity. Topological insulators and Weyl semimetals offer giant spin orbit effects for spintronics. Their surface states feature spin momentum locking, where spin is always perpendicular to momentum. This creates spin-polarized surface transport arising from spin momentum locking without requiring a ferromagnetic source. Effective spin Hall angles exceeding 1 have been measured, far surpassing conventional metals. The challenge is their typically high resistivity limiting practical applications. Comparing different material classes reveals trade-offs. Topological insulators like bismuth selenide have giant efficiency above 1, but resistivity around 1,000 microohm centimeters. Weyl semimetals like tungsten ditelluride offer intermediate efficiency around 0.4 with lower resistivity. Conventional tungsten at 0.3 efficiency with 150 microohm centimeter resistivity remains the practical baseline. Material selection depends on balancing efficiency against power consumption. The future of spintronics spans multiple directions. Materials innovation includes topological materials, 2D magnets, antiferromagnets, and the newly discovered altermagnets. Device evolution progresses toward SOT-MRAM commercialization, racetrack memory, spin logic, and neuromorphic computing. Physics exploration encompasses magnonics, skyamionics, and quantum spintronics. Applications expand to ultra-low power AI, quantum sensing, and edge computing. Several trends deserve attention. Altermagnets are a new magnetic phase combining antiferromagnetic order with spin-split bands, potentially offering the best of both worlds. Voltage-controlled magnetic anisotropy enables ultra-low power writing without current flow. Magnonics uses spin waves for beyond CMOS computing. Neuromorphic devices use magnetic materials to mimic brain synapses and neurons for energy-efficient AI. This Python simulation creates skyamion spin textures. The code calculates magnetization components from the skyamion profile function with specified helicity. Helicity distinguishes Neal type from block type textures, while reversing the winding number produces the anti-skyamion. The topological charge calculation confirms Q equals plus or minus 1. These visualizations help understand the distinct spin arrangements that define different skyamion types. Let's summarize the complete intermediate spintronics series. Chapter 1 covered spin-orbit interaction fundamentals including Rashba and Dresselhaus effects. Chapter 2 explained spin transfer torque theory and STT-MRAM. Chapter 3 presented spin-orbit torque and SOT-MRAM advantages. Chapter 4 surveyed advanced topics from antiferromagnets to 2D magnets. Together, these provide the foundation for understanding modern spintronics. Thank you for completing the Intermediate Spintronics series. For continued learning, an advanced series is planned covering magnonics, quantum spintronics, and computational methods. Related series on superconductivity and materials informatics are available. Key references include Manchun's 2019 SOT review, Furt's 2017 Skyamion review, and Gong and Zhang's 2019 2D magnets review. We hope this series has deepened your understanding of spintronics.